Welcome back, everybody. In this video, we're starting to work on section 4.3, which is about complements and conditional probability primarily, and then maybe a little bit of Bayes' theorem. So in the past sections, we were working on the addition rule for probability and a little bit of the multiplication rule for probability. In this section, the complements rule is basically going to give us a way of calculating probabilities indirectly. Sometimes taking an indirect approach is easier. And that's kind of where we'll start. So we've seen the multiplication rule that the probability of A and B is the probability of A times the probability of B given A. And then we use the OR formula to help develop the complements rule, and that is the probability of A complement plus the probability of A is equal to 1. And that's based on the idea that either A will or will not happen. And so we're sure of that, and so it has probability of 1. And when you have a probability of one thing or another occurring, that those two events, their probabilities are added. And since A and A complement are mutually exclusive, we don't have to worry about subtracting any kind of overlap. Okay, so in the problems that follow, we need to be careful with the wording. When you see a phrasing like at least one, that means one or more. In terms of math symbols, this would be greater than or equal to 1. At least one is one or more. The complement of at least one is none. So if you think about what is not true, if you don't have, that is, what is not true, if you don't have at least one, you'd have to have none. Okay, so let's try a example. So let's say a family has 3 children and we want to know the probability that they have at least one girl. So looking at this directly, I've got the sample space written out here. There's 8 possibilities, right? So the ones where there is at least one girl are those 3, and then all of those 4 in the second column. So out of the 8, 7/8 have at least one girl. So that's the answer. To illustrate the use of the complements rule to do this, if we wanted to know the probability of having at least one girl, well, what would it be like if that were not true? They'd have no girls, right? So this will be 1 minus the probability of no girls. Okay, just real quick, where is that coming from? Remember, the complements rule says that probability of A complement plus the probability of A is equal to 1. So if you solve for like P of A here, that means that we're going to subtract P of A complement from both sides. Okay, so that would be the probability of A is 1 minus the probability that A does not occur. So that's what we're going to use right here. Okay, so the probability of having at least one girl is 1 minus the probability of having no girls. And so that's 1 minus, and then out of the 8 possibilities, how is it that we could have no girls? There's only one way that could occur, and that's if there's all 3 boys. 1 minus 1/8, of course, is 7/8. So here the 2 answers, of course, will need to be the same. And in looking at this, when it looked easy enough just to take the direct approach, we'll see some problems here in a few minutes where it is much easier to take that indirect approach. Okay, this first example is just intended to be easier to illustrate the principle. Okay, so for the next example, we're going to roll some dice. So the story is 2 dice are rolled. We want to know the probability of getting at least a 5. So thinking about it, if you're going to roll at least a 5 using 2 dice, then you could roll a 5, 6, 7, 8, 9, 10, 11, or 12. And so if we were going to look at it that way, we'd have to figure out the probability of getting a 5 plus the probability of getting a 6, plus the probability of getting a 7, up to the probability of getting a 12, and then add together all those probabilities. So that's a lot of work. And so situations like that, where there's all these possibilities, we want to at least consider using the complements rule to get the job done. So let's try to take a second look at that and say, okay, what would it be like if we didn't have at least a 5? So the probability of getting at least a 5 would be 1 minus the probability that that doesn't happen. If you don't have at least 5, that means you have less than 5. Okay, so at least 5 would be 5 or more. If that fails to be true, then you have fewer than 5 or less than 5, and so that'll be 4 or less. Okay, and so it turns out that's easier to calculate. Okay, so I've got a table here off to the right showing the different possibilities ranging from rolling double ones, which totals 2, of course, up to double sixes, which totals 12. So it wouldn't be too hard to figure out this directly, given that we have the table here, but much easier to use the indirect approach. Less than 5, there's 1, 2, 3, 4, 5, 6 totals that are less than 5 out of 6 times 6, or 36 possibilities. That's 1 minus 1/6. That's 26. And so that is 5/6. Our probability of rolling at least a 5 would be 5/6. Okay. All right, let's try that again. Suppose that we want to find the probability of rolling at most 10. At most 10 would be 10 or less. We don't want to go over 10. So less than or equal to 10. So the probability of getting less than or equal to 10 is 1 minus the probability of, well, if that's not true, it's not going to include 10, right? Because at most 10 includes 10. If that fails to be true, then we have to be over 10. So this would need to be greater than 10, which is just 11 or 12, right? So 1 minus, there's 36 possibilities, and then we'll have only 3 that are higher than 10. Okay, so that's 1 minus 3/36. That's 1 minus 1/12, or 11/12. Okay, so that's another example of the complements rule. All right, so here's another example where we're going to use the complements rule. In this situation, it involves cards. So I've got a picture of the deck of cards in the notes for your reference. And so here we're going to draw 4 cards from this deck of cards, and we're going to do the drawing without replacement. So we've got a pile of cards here. We're just going to pick one card after another. We're going to do that 4 times. We want to pick 4 cards from the deck of cards without replacement. We want to know the probability that at least one is a face card. So you draw the 4 cards. What is the chance that you get at least one face card? So the face cards, of course, are the Jack, Queen, and King of the 4 suits. So there are 12 of those out of the 52 cards. What we're going to count as a success outcome is anytime you get at least one face card. So we want to think about how could we start on a formula for that? Well, at least one face card would be 1 face card, or 2, or 3, or 4 face cards. So there we'd have to figure out 4 separate probabilities and add them all up. So that could be more work. And so we're going to see about trying an indirect approach. Later on, I'm going to show you how this would look if we do it directly. But for now, let's see if we can do it indirectly. So we want to think about, well, what fails to be true if it is, or what's true if there's, if it's not true that there's at least one face card. Okay, so let's say that you're betting on getting at least one face card. Okay, if that doesn't happen, what's that look like? Okay, it's not 2 face cards, it's none, right? So the probability of getting at least one that's greater than or equal to 1 face card, okay, that's going to be 1 minus the probability of that not happening, which is getting no face cards. Okay, and so it's going to turn out that that's easier to calculate. Okay, so 1 minus, and then we need the probability of no face cards. So I need to think about what formula that is. If there's no face cards and we're drawing 4, that means there's first one is not a face card, and the second one isn't, and the third one isn't, and the fourth one isn't. So this turns this into an and problem. So we're going to multiply these probabilities. So first of all, we need the probability that the first one is not a face card. So out of the 52 cards, there are 12 face cards, so there are 40 that aren't. So the first non-face card, there's a 40 out of 52 chance of that first one not being a face card. We're doing our drawing without replacement, so there's only 51 cards left, out of which 39 are non-face cards. Continuing to draw, there will be 50 cards, out of which 38 are not face cards, and then 49 out of which 37 are not face cards. All right, so let me go ahead and calculate that for us and see what we get. All right, so going through the calculations, we end up with about 0.6624. So a little over or a little under a 2/3 chance of getting at least one face card when drawing 4 cards here without replacement. So make sure that you can enter this into your calculator and get the 0.6624, and then also make sure that you understand how this formula is working to help us get the answer. All right, so moving along, I want to look at a little at conditional probability. So that's next. So first thing to do is to remember the and formula, right? Probability of A and B. That's the probability of A times the probability of B given A. And so if you rewrite that so that the probability of B given A is isolated, this gives us a fraction, the probability of A and B divided by the probability of A. So this is a way for us to calculate conditional probability, and I wanted to show one example of how that works. So let's try it. Suppose that a die is rolled. We want to find the probability that it's a 5 given that it's odd. And this is a problem that's simple enough that we could do it by just drawing a picture and figuring it out, but I wanted just to illustrate how this formula up here in blue is going to work. Okay, so the probability of, let me first label some of these events. So let's say B will be get a 5, and A will be its odd. Okay, so then we want the probability of B given A. Okay, and so that's the probability of A and B. So if you roll a die, you're going to get a number 1, 2, 3, 4, 5, 6. You're going to get a number from 1 through 6. What is the probability that it's a 5 and it's odd? Okay, if it's 5 and it's odd, well, there's a 1 in 6 chance that it's a 5 and odd. So 1/6 in the numerator. Okay, down below, the probability of A, what is the probability that it's odd? Well, there's 3 out of 6 numbers are odd numbers, so there's a 1/2 chance that it's going to be an odd number. So we have 1/6 divided by 1/2. That's 1/6 times 2/1. That's 2/6, which reduces to 1/3, right? All right, so that's how the formula is going to work. The probability that it is a 5 given that it's odd. And this should be consistent with your expectations if we just kind of did this directly. Okay, so let's start fresh. We've got the numbers 1 through 6. The probability that it's a 5 is 1/6. Okay, if we're given that it's odd, so given that it's odd, if we're given that it's odd, it's one of these 3 numbers. Instead of being 1/6, it's now 1/3, right? So the probabilities are half as much, which is why in the formula above, we divided by 1/2 to decrease the number of possible values. So 1/3, okay? All right. So often we'll be figuring out conditional probabilities just as we did here, kind of more or less in pink, or using a table. But there are times when using the formula is also helpful. Okay, So now we're going to draw a card. We're going to figure out the following probabilities. So you should take a minute and calculate these probabilities yourself and then see what you get. Okay, so pause the video, try that, and then restart it and see what you did. All right, so we want to figure out the probability of getting a heart. The probability of getting a heart is 1/4. There are 4 possible suits. One of them is hearts, so it's 1/4 chance. Okay. The probability of getting a red card. Well, half the cards are red and half are black, so the probability is 1/2. Okay, the probability of getting a heart card, given that it's red, okay, the probability of getting hearts, given that it's red, is 1/2. The probability of getting hearts was 1/4. If we give you the additional information that it's red, then that decreases the number of possibilities because now we know it can not be spades or clubs. Okay, the probability that it's red given that it's hearts, well, that's certain, right? If we know that it's hearts, then it's definitely red. Okay, you'll notice that these 2 probabilities are different from each other. You want to make sure that you understand the difference between the probability that it's hearts given that it's red and the probability that it's red given that it's hearts, because they can kind of sound alike, but as you can see, the 2 numbers are different. Okay, and that leads us to the idea of the confusion of the inverse, which is kind of a fun sounding name, but basically it reads like this, that if you're prone to confusing the probability of A given B and the probability of B given A, that's the confusion of the inverse. So to illustrate that, we're going to go back to our drug testing example that we had before. So we had seen this table back in earlier in chapter 4. And there's 4 possibilities here. We have columns for positive test results and negative test results, and rows for whether or not the test taker actually does or does not use drugs. And so we've seen all of this data before. So we're going to find, first of all, the probability that a subject uses drugs, given that they have a positive test result, and then the probability that they have a positive test result, given that they use drugs. So we want to figure out those 2 probabilities. So let's do that. Okay, so the probability that somebody uses drugs was 50 out of 1,000, right? There's 50 drug users out of 1,000 total test takers. But if we're given that they have a positive test result, okay, that means that they belong to this first column. There's only 134 people in that column. Okay, and the probability that the person actually uses drugs there is 44. So that's 44 out of 134. And that's about 0.328. Okay, now we want to look the other way and say, well, what is the probability that they got a positive test result given that they use drugs? So there are 50 drug users in our survey. And out of those 50 drug users, the chance of a person testing positive is 44. So that's 44 out of 50, and that's 0.88. So clearly you can see that those 2 probabilities are different from one another. And so that should illustrate that the placement, that is what you're given, matters. So the probability of A given B is not the same in general as the probability of B given A. All right, so that takes us to the end of our first part of section 4.3. We'll have more examples to come in the next video. In the meantime, let me know if you have any questions, and have a great day.